Today we're going to finish up the notes from Chapter 2. We're still talking about kinematics, or the motion of objects. We'll just introduce objects that are in free fall, and we'll talk more about motion graphs. So an object that is in free fall has an acceleration of 9.80 meters per second squared here on Earth. This is a constant that is written on your equation sheet, so it's not something you have to have memorized, but likely you will have it memorized just because we'll use it so often. It's often labeled with a lowercase g, so g equals 9.8 or negative 9.8 meters per second squared. That negative comes from the direction, so this is a downward acceleration. So typically downward is the negative direction and upward is the positive direction. It's called free fall because there are no other forces acting on the object. So there's no air resistance or drag. And again, we can assume this is a constant acceleration. So that acceleration happens or acts on the object while it's moving upward in the air, while it's coming down. If it's moving sideways, there's always this downward acceleration. So here we have our first example problem. Again, go ahead and pause the video and then resume once you're ready to check your answer. All right, so first I've gone ahead and labeled some of the values that are given in the problem. I have separate values here for y and y naught. Sometimes, well, actually often I will just write this as a delta y. One thing to be very careful with, a lot of times people will make a mistake initially, and they'll see that there's a positive height here. So they think of, the height of 125 meters as a positive value. But keep in mind, this package is dropping that distance. So it's moving that distance downward. So if I were to write out the delta y, I would want to write it as a negative value. So I have a delta y of negative 125 meters, or y naught as 0 and y as negative 125. You could also do y naught as 125 and y as 0. That works as well. V naught is a positive 5.2 since that's an upward initial velocity, and the acceleration negative 9.8 or 9.80 if you want. That's negative since it's downward. Here we have the kinematic equation. This is on the equation sheet. It is written with x's instead of y's on the equation sheet. I just used y's since this is in the vertical direction, but you can write it as x if you want. Plugging in the values. And if you notice, we get stuck here. We end up with a quadratic equation. This is where it's good news. You can use your graphing calculator, since you'll only likely see quadratic equations on homework problems. You can go ahead and search up a website to solve quadratic equations, plug in the values, and you should get a time. If you get a negative time, just ignore that. Typically, there's just one time that will be the actual answer, and another one would be like as if you went back in time, but obviously that's not going to happen. All right, concept check. So first, if the velocity of an object is 0, does it mean that the acceleration is also 0? No, not necessarily. And one common example that can also trip people up, if you toss a ball straight up into the air, at the topmost point, its velocity is 0. It's no longer moving up, hasn't yet started moving down, but the acceleration at the top is negative 9.8 meters per second squared. If acceleration is 0, does it mean velocity is also 0? Also, no, you can have velocity. If you have constant velocity, that means you're not accelerating. So, for example, driving forward with constant speed. And this is an activity we would typically do in class. It says, how can you determine your reaction time without a stopwatch? And will it be different on the moon? So for this activity, you have just a meter stick, and generally with a partner, your partner will drop the meter stick without giving you any warning, and you will close your hand to grab it, keep it from falling as quickly as you can. And then if you measure the distance that it falls, or displacement, we can use delta x equals v naught t plus 1/2 at squared. If it's dropping, that means v naught is 0, and we know the acceleration as it falls is that negative 9.8. So you can use that to solve for time, and that time is the time it fell before you were able to react. Maybe tougher question, will it be different on the moon? So if you think about it, your reaction time should not be affected by whether you're on the Earth or the moon. So the time should not be different. What is different is the acceleration of gravity on the moon. It's much less, which means the distance that the meter stick will fall will be less as well. So those two variables will be smaller, but they do not affect your reaction time. All right, here we have a more complex example problem. So again, go ahead and pause and resume when you're ready. So we're trying to find the speed of the water as it leaves the hose nozzle. And the main things we are given here are the initial height of the water is 1.5 meters. Keep in mind, again, if we're looking at the displacement of the water, it's a negative 1.5 meters because it ends up lower than where it started. And we know the time it takes to go from where it leaves the hose to where it hits the ground is 2 seconds. So I'm using this equation. It's the same one we used before. I did just write it as delta y this time instead of y equals y naught plus v naught t plus 1/2 at squared. Plugging in the values, and I solve and get v naught as 9.05 meters per second. All right, so some common problems. One of them I've already mentioned, so be very careful about the delta x, the displacement or distance that an object moves. If an object is dropped, keep in mind that the displacement is downward. Some other issues students typically have are picking out the correct equation. So just to kind of summarize, we have these 3 different equations for kinematics on the equation sheet. There's a 4th one, that's the average velocity, or v plus v naught over 2 equals delta x over delta t. So that one's not on the equation sheet, but you can use that one as well. All of these equations have 4 of the 5 variables in them. So there's 4 of the 5. That means you need to know 3 of them to solve for the other variables. So generally what you should do first is identify the values given to you in the problem, and make sure you're careful checking for things like if it's dropped, which tells you it starts from rest. If it's in free fall, that tells you the acceleration. So sometimes there's quantities given that are not specifically written out as numbers. So you should hopefully be able to find 3 different quantities, and then from there on, next step would be to pick out which equation has those quantities and what you're trying to solve for. If you can't find an equation that works, you may need to solve it in 2 different steps. So you may need to solve for a random 4th variable first, and then once you have 4 variables, then your options are a lot greater. The last bullet point there is very important as well. Be very careful with positive and negative values. Again, if it's fired upward, then it will have an initial positive velocity, but a negative acceleration. And then the displacement will depend on if it ends up higher or lower than compared to where it started. All right, our other topic for today is motion graphs. So we talked about graphs a little bit before. One common thing you'll need to do with graphs is find the slope, and you should always use points from the line to do that. So here we have a position time graph, and if you have a position time graph, the slope, which is the change in the y-axis over the change in the x-axis, here that slope would be the change in x over the change in t, right? Or delta x over delta t. And you should recognize that as being equal to the velocity. So the slope on a position time graph gives you the velocity. If it's a straight line, that means we have a constant velocity. So here we have a graph showing a constant velocity of about 11 meters per second. We don't always get a nice, perfect straight line. So here we have a couple examples of slightly more difficult graphs to interpret. And note that on the left, we have a velocity time graph. So when we're looking at the graph on the left, we'd probably break it down into different segments. Here, those segments are numbered 1, 2, 3, and 4. If I'm looking at segment 1, I can see that the velocity goes from 0 meters per second to 15 meters per second. That means it starts at rest and speeds up. Between A and B for segment 2, we have a horizontal line. If you think about it, that means this velocity here is staying constant at 15 meters per second. So if I wanted to know the distance it traveled here, I could just say 15 meters per second equals the distance or displacement over the time. In segment 3, the graph goes down. If you look at values, that the velocity goes from 15 meters per second down to 5. That means it slows down. So here this negative slope tells you it's slowing down, right? It's not actually turning around. It's still moving in the positive direction. And then we have another constant velocity portion in segment 4. On the right, we have some curved lines. And so if we wanted to find the slope, in this case, because it's a position time graph, the slope would give us the velocity. We could draw in a tangent line. So one of those tangent lines is drawn in for you for the slope at t equals 10 seconds. And if you want to go to the PowerPoint on Canvas and click on that link to interactive motion graphs, that will take you to a site where you can just see what different graphs, position, velocity, and even acceleration graphs look like for objects that are constant velocity or accelerating. All right, so I mentioned before, if you have a position time graph, the slope gives you velocity. If you have a velocity time graph, the slope gives you the acceleration, and the area under the curve, what's shown or to be estimated with those pink rectangles, the area under the curve gives you displacement. So if you've taken calculus, that's the integral we're looking at here. It's kind of like going backwards from slope. So slope of a position time graph gives you velocity, and the area of a velocity time graph gives you position or displacement, really, the delta x. One thing you should be somewhat familiar about, so if we just have a graph like this, if you wanted to find the area, you'd really most likely break this apart into different triangles and rectangles. You should be comfortable finding the area of triangles and rectangles, so you could find the actual area that way. If these were curved lines, one way you can approximate the area is by using these narrow rectangles. So, on the top, if you imagine this is a curved line, having wider rectangles will give you an estimate, but maybe not a very good one. And the narrower these rectangles are, the smaller delta t we use, the more accurate the estimate will be. Okay, here we have another example problem. So we have uniform acceleration from 0 to 10 seconds, but we're only looking for how far it moves from 2 to 6 seconds. So kind of partway through that acceleration. So first step is I solve for the acceleration just using the change in velocity over the change in time. So we get 10 meters per second squared. Next, I'm going to look at the motion before the time segment we're really looking at. So for the first 2 seconds, I'm going to figure out how fast it's going at the end of those 2 seconds. So I end up with 70 meters per second. And now I'm looking at the segment just from 2 to 6 seconds. So that sort of final speed from 0 to 2 is now my initial speed if I'm looking at 2 seconds up to 6 seconds. So to find the displacement or distance that it moves, since it's just going in a straight line, distance, displacement, same thing. I have delta x equals v naught t plus 1/2 at squared. Plugging in my initial speed now at 70 meters per second and a delta t of 4 seconds, we end up with 360 meters. So we're going to do that same problem, but now we're going to look at solving it with a graph. So again, pause and resume the video when you're ready. So I've gone ahead and labeled the graph here, velocity on the y-axis, time on the x-axis. Here we have a line showing the motion. Since it's a uniform acceleration, I can draw a straight line, and we know it starts at 50 meters per second at 0 seconds, and it ends at 150 meters per second at 10 seconds. And I'm only looking at the segment between 2 and 6 seconds. So that is this shaded region. So this shape is a trapezoid. To find the displacement, I just need to know that area. If you know the formula for calculating the area of a trapezoid, great. It is y1 plus y2 over 2 and then times delta x. If you don't know the area for a trapezoid, you can break this down into a rectangle and a triangle sitting on top of it, and then just find the area of both separately and combine them together. So we have 70 and 110. Those values you would either just have to estimate from this graph, or you could calculate. The 70 we already calculated previously, and we end up with an area of 360 meters. So same as previously, of course. All right, here's another example problem. For questions A, B, and C, we are looking at just this first segment between A and B. We'll then look at those same 3 questions for segments C to D and then D to E. So pause and resume when you're ready. So from A to B, it's moving in the negative direction, right? It's moving toward our origin, toward 0. The object is speeding up. So when we have a flat horizontal line on a position time graph, like we do at the beginning of this graph near A, that tells us the position is staying constant, right, at 25 for the first few milliseconds at least, which means it's not moving. So it's not moving, and then it starts to speed up toward our origin, or toward wherever 0 position is located. And because it's speeding up in the negative direction, that's a negative acceleration. For C to D, it's not moving at all, right? The position is staying at 5 meters, so no motion, no speeding up or slowing down, and no acceleration. So either it does not apply or it's 0 for each of those questions. And the last segment, D to E, here we have the object moving in the positive direction, so it's moving away from our origin. The position is getting larger or increasing. It's speeding up, and acceleration is also positive. All right, so here we have another graph, and what I want to talk about with this slide is just that sometimes rather than trying to interpret the graph by picking out slope or area, sometimes it's easier to just pick out values. So we're going to go ahead and do that here. So the first question is, which variables are known? And I've gone ahead and written out all the variables that we typically would use with accelerated motion. So v, v naught, a, delta x, t. Which of those can you pick out from the graph? And then from those variables, which equations might you use to solve for other values? So I'll give you a second. So just to be clear, if we're looking at this full line, all of these variables can be determined, but there are some that are just really easy to pick out and others that you have to actually calculate. So I'm only going to list the ones you can pick out without doing any calculation. So v, that's your final velocity, so that's obviously -10 here. V naught, that's +10, right, the starting velocity. Time, that's 3 seconds. All of those you can figure out just by looking at the line itself, not doing anything else. Of course, a, that acceleration is the slope of the line, so that's not very hard to figure out. And delta x, that would be the area under the curve. So you could figure that out as well without too much difficulty. But these are the three variables we can easily pick out. And those three variables show up in one of our equations. So we could very quickly solve for acceleration using that equation as well. So sometimes it's easier to pick out values from the graph. The other one, this one's not listed on the equation sheet, but again, it is sometimes helpful to use. This comes from average velocity equals delta x over delta t. And we don't always write the delta with a t, but the time is always from a starting point to an end point in time.